yesterday. Just to remind you, we're talking about, can you hear me? Is that okay? Okay. We were talking about Poissonbottom equation. We deduced Poissonbottom equation. Actually, we deduced the Boltzmann distribution, and together with Poisson equation, we got Poissonbottom equation. And then we discussed that we needed to modify the Poissonbottom equation in order to get the Hofmeister effects, the ion-specific effects. And what we wrote down yesterday was that talking about potential of mean force, what we have is a Hamaker contribution that actually is van der Waals contribution, van der Waals energy between two particles, for example, plus the electrical contribution and the hard sphere contribution. So we wrote down these two, and we are studying this one, the contribution of the double layers that form around the two particles, for example. So we have here two particles. We have a double layer around this and another double layer around this. And when these colloidal particles are immersed in an electrolyte solution, the interaction actually is between those two double layers. So we need to account for this using Poisson equation. And in this first approach, we used Boltzmann distribution as well. So today, we are going to modify the Poisson-Boltzmann equation in order to take into account ion-specific effects. Okay, so we're going to deal with the modified Poisson-Boltzmann equation, and then we will have an introduction to the classical density functional theory, and we are going to discuss a little about size and electrostatic correlations. Okay, so the modified Poisson-Boltzmann equation. So we have here an improvement. We have to do modifications in order to take into account several important effects that are not accounted for in the classical theory. For example, dispersion forces, hydration, ion size effects. Yesterday, I think I forgot to say that in the Good-Chapman approach that we used to derive Poisson-Boltzmann equation, we consider point charges. So our ions have no size. So now we are going to consider ion size effects. We are going to see how to introduce it in Poisson-Boltzmann equation. And also, we are going to see somehow how to try to introduce the electric correlation between ions in the Poisson-Boltzmann theory. We're going to discuss this strategy. And these additional contributions that we're going to study today can be divided in two classes of contributions. We have the external field contributions, for example, the interaction between ion and surface, ion and interface. And we have what we call the residual chemical potential contribution that accounts for multi-body effects, the interaction among the molecules or the ions. Okay? So we come back to that expression that we used yesterday. We can see here, yesterday we wrote down this one, the reference chemical potential plus KBT ln of Ci. Somebody asked me why didn't I use activity here instead of concentration. Actually, this classical model, the classical model that we used yesterday, we wrote until here, consider that the only known ideality of the system was due to the ion charge, okay? Except for that, we are considering an ideal solution. So now we are going to introduce other known idealities. For example, this UI, there is the external potential, and this residual chemical potential. When we do exactly the same that we did yesterday, considering that the chemical potential is equal in any point, including at bulk, we have this equality, and then we solve for the concentration of ion, Ci, the ion concentration. So we get this expression here. If we compare to that we got yesterday, we have this one, there is new, and this one, and all of this, okay? Here, what we got yesterday was Ci equal to Ci C infinity I, exponential of minus Zi psi kBt. So yesterday we had this one, that was the classical Boltzmann distribution, and now we have this modified Boltzmann distribution. This psi infinity usually is equal to 0, because if we are at bulk, we have no electric field, so coming from the surface, so we consider that it's 0. But if we are at a distance that is not so far, we can have a residual contribution here, okay? So here we have the modified Boltzmann distribution, and if we introduce this modified Boltzmann distribution on the Poisson equation, we have the modified Poisson-Boltzmann equation. And we can see here that in this version, I introduced also this rho f, okay? This rho f is the volumetric charge density of fixed charges. So we use this when we want to describe, for example, proteins inside a cell, when we are trying to solve it inside and outside a cell, as I will show me, and Natalia is also going to show this tomorrow. So we describe those proteins, for example, as fixed charges, as we're going to see tomorrow, okay? And this is known a priori. We suppose that it's a function that we know a priori. And what we calculate is the mobile charge distribution from this modified Poisson-Boltzmann equation. And the boundary conditions are exactly the same as we studied yesterday. So we can consider specified potential at the surface and at bulk, or specified charge at the surface and at bulk. So accounting for these modifications, we can have this kind of contribution. There is the external potential that can be somehow like this. This is the ion dispersion interaction between an ion and the surface. We saw this yesterday when we saw that table with the many expressions. So when we have an ion interacting with a flat surface, we have a function that is proportional to 1 over x to the cubic, x cubic. And we have this Bi, that would be the ion dispersion coefficient. And this function g of x here, it was introduced just to avoid that the energy goes to infinity at closest approach distance at adhesion. So this one gives a finite value to the dispersion interaction when we have the ion very close to the surface, okay? And just to check for other geometries, if we have, for example, bispherical coordinates that I will show you tomorrow, we can write this one. So this is the same Bi, the same kind of dispersion coefficient that is calculated, for example, from Lifshitz theory that considers the polarizability of the ion and also dielectric constants of each medium. So this is for one sphere, and this is for the other sphere. This is the radius of the first sphere. This is the radius of the second sphere. And this is the distance between the ion and the sphere. When we are talking about R, we are considering center-to-center distance, okay? So this is R. And when we have D or L, in some places you see D, in other places you see L. It's the surface-to-surface distance, okay? If you have this one, for example, from between two particles, this is the surface-to-surface distance. So there we are talking about center-to-center distance. And we can also do what we call a scale integration, okay? We can use, Fernando talked about this in one of his talks too. We can get information from a more detailed simulation and introduce it in a macroscopic model, for example. How do we do that? We get, for example, potential of mean force of an ion at infinite dilution interacting with a surface. So we have this kind of expression for the potential of mean force. Don't bother about the coefficients here, the parameters, because we only use them in order to turn continuous results that are not continuous. So just to get a function so that we can use it in a continuous theory. And we account for the interaction of the ion and the first interface, and this is the interaction of the ion with the second interface as a function of x. So what we get here is the total interaction between the ion and the two surfaces, okay? So we are considering here that we have, for example, two plates and the ion here. So we have a distance to each interface, to each surface. So this is L, this is not L, this is X. So this is X, and this is L minus X, and L is this distance. Okay? So we get those information from molecular dynamics simulations, and we introduce them in Poissonbottom equation. So these interactions account for van der Waals interactions, ionic hydration, and also self-image charge potential. Okay, so this is the image that the ion creates at the surface because of the interaction of the ion and the surface, disturbing the dielectric constant at that point, for example. And by doing this, we introduce at the same time many different other interactions of the ion with the surface. So these are all introduced as external potentials. Okay. If we wanna count, take into account the ion size, we can use this approach. So we have here Wy. There is a function of concentration and surface charge. And this is the same quantity, but at bulk. So how can we calculate that? We can use an equation of states in order to account for ion size. For example, an equation of state for hard spheres. So we can introduce the so-called Bublik-Mansouri-Carnot-Steiner-Land equation of state for a hard sphere. So we have this equation, and we have to introduce it inside Poissonbottom equation. The computational cost increases a lot when we do that. Why? Because this function is a function of concentration. And we are using this in order to find the concentration profiles, the ion profiles. So we need to solve it iteratively, or we need to use a kind of differential algebraic approach that is not so fast as well. So when we do that, the computational effort increases a lot. And there is somehow a kind of proposition by Bazin and co-workers that try to introduce ion correlation in Poissonbottom equation. How do they do that? They introduce this contribution here that turns the equation into a fourth order differential equation. So it's equivalent to the so-called Poisson-Fermi equation, okay? And we get this scaling factor. There is an empirical parameter that should establish until where the ion-ion correlations are relevant. The problem is that this parameter usually is used as an adjustable parameter. And by doing that, we somehow get a kind of empirical model. So if we use this as a fixed distance from other knowledge, so it's more or less okay. But if we use this as an empirical parameter, I don't know if it's worth it, okay? So the problem here is that, again, the computational effort increases a lot. So here is the same equation written in Cartesian coordinates. And the boundary conditions, we need now 2 additional boundary conditions as we have a 4th order differential equation. So we introduce other boundary conditions. For example, we say that correlations are neglected at the surface. Why? I don't know. I don't agree with that. But that's what they usually do. And what we can do with Poissonbottom equation as well is considering charge regulation at the surface. Fernando talked about this yesterday. So he showed this kind of expressions considering the chemical equilibrium at the surface. As he talked yesterday, we usually use activity here. So when we use concentration, it's what he calls, you call stoichiometric approach. So we are considering here the concentration of hydrogen isotopes, but this is the surface concentration. So it's calculated from pH, of course, and also considers the surface potential. Okay, so the pH, we must remember that the pH at the surface is different from bulk pH. So we are considering this. And if we sum up all the contributions, we have the average surface charge. Okay, so from this, when we are using this, we follow the proposition by Ninhan and Parsegian. And by doing this, we can calculate, as Fernando showed yesterday, the titration curves of different proteins. So this would be the lysozyme titration curve, and this is BSA. We here are not considering, for example, neighborhood effects, as Fernando showed yesterday. So we have here, in these calculations, we have an isoelectric point of 11.2 for lysozyme, and another isoelectric point for BSA, there is kind of 4.6, okay? What is the isoelectric point? I think you know that, but it's the point where we have potential equal to 0 at the surface of the protein. The liquid charge is equal to 0. So here we can calculate, for example, from this modified Poissonbottom equation, we can calculate the force between particles. We are going to see how to apply the Poissonbottom equation by spherical coordinates tomorrow. But I bring here a result obtained with this kind of coordinate system. And so we calculate the force between a BSA and a lysozyme, okay? So we have a lysozyme interacting with a BSA, and we are calculating the force between them as a function of pH. Okay, so we have a fixed distance, and we are calculating the force as a function of pH. Tomorrow I'm going to give more details about the conditions considered here, but today I only brought this to show you that when we consider these kind of interactions, and here we consider only the dispersion interaction, the ion dispersion interaction, the van der Waals interaction between ion and surfaces, and both surfaces, we finally get the ion-specific effects. So what we have here is sodium chloride, sodium bromide, sodium iodide. This NP corresponds to non-polarizable ion, so it would be the ion of the classical Poissonbottom equation that has no polarizability. And we can see that we have different curves for those different salts. And when we have only one protein, for example, only, yes, Leandro?
I'm sorry, just to be, but sometimes we know that there are some reports in the literature that BSA may have a very, very huge dipolar moment in the charge distribution on the protein surface. Is this model taking this into account, or
no,
spherical symmetrical distribution?
Yeah, it considers symmetry, so we are not taking into account this dipole contribution. Okay. So here, we can see that we have different curves for those different salts. And if we have, for example, only one protein, for example, lysozyme, the inversion of Hofmeister series usually happens around the isoelectric point. So for lysozyme, it would be around 11.2, and for BSA, it's around 4.6. And when we introduce two different proteins, the isoelectric, the inversion of the Hofmeister series that occurs here occurs in between those two isoelectric points. Okay, so we can see that we have a reversed series in this side.
Sorry.
Yeah.
That was very curious. When you have the zero force, you are saying to me that before that point you have, let's say, repulsive force. After that you have attractive force.
Yeah, that's a good question. Thank you. That's a good question. I forgot to say that. So here, when force is zero, we are saying that we have equilibrium. So a negative force, so on this side we have attraction, and here we have repulsion. So if we compare this to this titration curve, we see that when we have a pH that is lower than 4.6, both proteins are positively charged, so we have repulsion. It's this region. Here, above 11.2, we have both proteins negatively charged. So again, we have repulsion. And in the middle, we have attraction because one of them is positive and the other is negative. Okay. Of course, it's not exactly at the isoelectric point that force is equal to zero because we are considering also other contributions. Okay. Any other question before I move to DFT? Okay. So now I'm going to talk about density functional theory, and I criticized a little some approach to using Poissonbottom equation, especially because of the computational time, the computational effort required. And what we have when we use density functional theory is a more detailed calculation. It somehow requires a higher computational effort too, but it's much lower than the effort required, for example, by molecular simulation. So we base our studies in this kind of sentence, for example, by van der Waals. He said that, he concluded that matter distributes itself in space in such a way that for a given energy, so specified energy, the entropy attains a maximum. So the variation of entropy as a function of density profile is equal to zero, as we have a maximum. So this is sufficient, but not sufficient. This is a required but not sufficient condition for the maximum. Okay, so if we have specified energy, we deal with entropy. If we have, for example, temperature, volume, and number of particles, we deal with Helmholtz free energy. And if we have temperature, volume, and specified potential, chemical potential, we deal with the grand potential. Okay, so that's what we do, for example, when we are calculating equilibrium, when we specify chemical potential. And I'm going to talk about the classical DFT. So here I compare the classical DFT with the electronic DFT. The classical DFT is applied to calculate structure and thermophysical properties. And while the electronic DFT, also known as quantum DFT, is applied for spectroscopy, electronic, and optoelectronic properties. So when we apply classical DFT, we deal with density of matter, and for the electronic one, we have electronic density. And you can see here that both are related to Nobel Prize. Of course, they didn't get the Nobel Prize exactly for this study, but we only relating that many people that got Nobel Prize also dedicated sometimes in studying DFT, okay? So for the classical DFT, we calculate structures and thermodynamic properties from a molecular perspective. It can be applied to several systems, for example, polymers, polyelectrolytes, electrolytes, biomacromolecules. It takes into account macroscopic details without dealing with thermal fluctuations, so that's why it's much faster than molecular simulation, for example. Okay. So it's a middle term between Poissonbottom approach and molecular simulation. Okay. So we base DFT on this, the so-called Homberg-Kohn theorem. It was originally proposed in quantum mechanics of the ground state energy of electrons at 0 Kelvin. Then its generalization was shown to finite temperature by Mermin. And finally, Evans in 1979 showed that it is equally applicable to classical systems. So that's the version that we use, the classical DFT. And this theorem says that the one-body potential can be uniquely determined by a density profile that minimizes the grand potential functional. Okay, so the consequence is that we have the Helmholtz energy that can be expressed as a unique functional of the density profile. So if we know a density profile, we can calculate a Helmholtz energy, and we can try to find the density profile that minimizes this Helmholtz energy depending on the ensemble, the Helmholtz energy or the grand canonical potential. Okay, so we base our studies in these references here, especially Evans. And so the Helmholtz energy is considered as functional of the density profile. So that's why we call density functional theory. And this function that describes the density is actually an ensemble average of the instantaneous molecular densities. So we don't deal with these instantaneous molecular densities, but with this ensemble average density. Okay. So this is the Legendre transformation that links the grand potential with the Helmholtz free energy. And here we have the density profile and the external potential and chemical potential. And this difference gives the so-called one-body potential. Okay? And in order to solve DFT, we are going to try to find a minimum in this functional of the grand potential. So what we need to do is a functional derivative of this function. And we have that at the minimum, this is equal to 0. And by solving that, we find the equilibrium density profile. This is the so-called Euler-Lagrange equation. So here we write it in terms of free energy. We just have to introduce this equation in this derivative here. So we have this equation. And the ideal contribution is well known. So we can solve it analytically. We have this expression. And by introducing this expression to this equation and solving for rho of R, we get the expression for the ionic profile or for the molecular profile. So we have this exponential here, and we see that we are getting somehow something that is similar to what we got in Poisson-Boltzmann theory. We are going to compare these two, okay? So when we talk about Helmholtz functional, we can separate in different contributions. So we have the ideal contribution and also many different excess contributions. And here we separate, for example, the hard sphere contribution, the direct Coulomb contribution, and here's the electrostatic correlation contribution. And the electrostatic contribution is composed by two contributions. And these two contributions are the direct Coulomb contribution and the electrostatic correlations. Okay, so that's why we separated these two. So using the same notation that we used for Poisson-Boltzmann theory, we can write down this equation, this expression. So here, again, we have chemical potential, external potential, and here's the functional derivative of the excess Helmholtz potential, energy, Helmholtz energy. And defining the mean electrostatic potential, there would be this external potential plus the direct Coulomb contribution, we see that we get a very similar expression to the Boltzmann distribution. And when we neglect size correlations and electrostatic correlations, we get exactly the same expression that we considered last class, yesterday. Okay, so this is again the classical Boltzmann distribution. So we see that the difference between this DFT approach and the Poisson-Boltzmann approach are these two terms, the electrostatic correlations and the size correlations. Okay. To account for the size correlation, we use the same equation of state that I showed before. Yes, yeah, it's this. So we can use, for example, these three approaches here, FMT. So it's the so-called fundamental measure theory by Rosenfeld. And there is another approach proposed by Forsman and Coworkers. And we use also, that's the one we use, the so-called white bear. There's a modified FMT using that same equation of Bublik, Mansouri, Carnahan, Starling, and Leland equation of states. Okay, so that's how we account, and this comes naturally. This is naturally introduced in the DFT theory. And also to account for electrostatic correlations, we have many different approaches proposed in the literature. So if you see many different DFTs, they are different because of those different approaches. Okay. We need to express these functionals. So there are many different approximations that are proposed in the literature. So we have many different approximations, as for example, weighted correlation approach and bulk fluid density approach. We have contact corrected DFT approach and reference fluid density approach. Okay, and finally the whole correlated biochemical theory. So these are all different ways of accounting for electrostatic correlations. Let's think about what's electrostatic correlation. How can we account for electrostatic correlation? How would you explain electrostatic correlation, ion-ion correlation? When I try to do that, I always remember Professor Holland Schillender talking about this, and he says that imagine that you can sit on an ion, and you are counting what, how many neighbors you have, and how their movement, their interactions, is going to affect your position and your charge. So it's a multi-body effect. That's why we call electrostatic correlation. It's a many-body effect. Okay. So DFT summing up, we do something like this. We needed to have an expression for the Helmholtz energy, functional. So we have in the literature many propositions for this expression. Once we have an expression, we minimize the ground potential, and by minimizing the ground potential, we get the equilibrium density profiles, and from this we calculate thermodynamic properties. Okay. And how do you do this numerically? The conventional method to converge to the equilibrium densities is one of them is the Picard method. This convergence is not easy to be done. So what we do is we mix two different solutions. So we have the old dense profile, that is this one, and we solve the Euler-Lagrange equation, find the equilibrium density, so we have a new density, okay? So this is this rho I out. So this new density needs to be mixtured with the old density profile. If we get only this new density profile, it won't converge. So what we do is using an F parameter that we call a mixture parameter. You're going to mix, interpolate the old solution and the new solution. And usually we use a very low F. There are ways of calculating the best F, but sometimes we use, for example, F equal to 0.002. It means that we are considering only 2% of the new solution and mixturing it with the old solution so that we can get convergence. So sometimes it's not so easy to obtain this convergence. It's a kind of successive substitution method. And here I'd like to show some results applying the classical theories. Okay. So this is a comparison between Poisson-Boltzmann and the Biocolloidal and DFT. The Biocolloidal equations, just to remember, last class we saw that it is the linearization of the Poisson-Boltzmann equation. And we can see that for this 1 south, a low electrostatic potential, a low concentration, we get the same result for DFT and Poisson-Boltzmann. And the Biocolloidal is also not so different in this case. But when we consider, for example, a 2 south, at the same condition, we can see that there is a higher difference. Here we have Poisson-Boltzmann, this is DFT, and the Biocolloidal. We can see that DFT here is located between the Poisson-Boltzmann and the Biocolloidal. And in this case, the Biocolloidal get good result for lower distance because of the compensation of errors. There are many errors in this theory, so they compensate each other so that the result's not so bad. But you can see that for a higher concentration, it's not that good. And if we increase again the concentration, for this case, again for the compensation of errors, we get similar results for DFT and Poisson-Boltzmann. And these are some results comparing with molecular simulation. Okay, so this is for comparing with Monte Carlo simulation. This is a 1 south with 0.35 density charge. And an increased concentration, this is a higher concentration, and we get those results. So Poisson-Boltzmann shows very different results at lower distances, but DFT reproduces almost exactly the molecular simulation results. Okay, so in this case, we have a successful application of DFT, and the advantage here is that it is much faster than molecular simulation. Okay. So that's what I was planning to discuss with you today. Fernando asked me to be a little faster today. And so, but we still have time for questions. So if you have questions, please make your questions. If you want to, yeah?
Just like I didn't, in the Picard method, I didn't really understand how it's supposed to work.
Picard method?
Yeah.
Okay, let's return to that.
I didn't understand what is the raw in, raw out, and the
Ah, okay, okay. In order to start applying the method, we need an initial guess. So for example, let's suppose you propose that your initial functional is equal to a constant. So you have a profile that is a constant, and you introduce this, and from this you calculate all the functionals, and you solve DFT and find the minimum, and from this minimum you have a new profile. For example, let's say that the new profile is something like this. Okay? So if we go straight to this new profile and do it again introducing this new this new profile in the functionals and solving again, we usually don't get convergence. So what we do is interpolating these points and get a profile that is in a middle term between these two profiles. Okay, so this is done with a linear interpolation using this called mixture parameter. If we use, for example, 0.05, you're considering 5% of the new solution of this new profile and 95% of the old profile. If you use 0.5, you are considering both. So you can adjust this F parameter in order to have convergence. If you use a too low parameter, the method is very low. It takes a long time to be solved. But on the other hand, if you use a very high parameter, you usually don't get convergence. Okay. Other questions? Yeah.
I'm guessing that you use a fixed mixture parameter along the whole simulation, right?
It depends on the approach. We can use a fixed parameter, but we usually, by using a fixed parameter, we have a very time-demanding simulation. So we can calculate new parameters for each iteration. So that.
So you can use a predictor corrector approach, and so you can adapt your parameter to the velocity of your convergence.
Yeah, it's a kind of predictor corrector approach that you can use. Okay.
I'm particularly interested in the analysis of BSA interaction force calculations. Are those very expensive from the computational point of view, or they are, let's say, quick?
Well, it depends on what resource you are using, of course. For example, just to compare, I did that in 2007, okay, with the best computer that I had, personal computer that I had in 2007, and to have that whole curve, I got 48 hours, okay? But my student did that 2 years ago, and it took 2 minutes. Okay, so it depends on the computational resource. So now it's not so time demanding.
Because I was wondering, since BSA has this huge dipole contribution, it was possible to try to adapt your model, including a dipole charge interaction, because like a 1 to r to the third power, and something like this, to try to get this in consideration. But in that way, of course, it will depend on the orientation of your dipole and with respect with your charge. So you have to fix the distance and try to do like an integration in 4 pi or something similar to this to try to get this information. Do you think that this should be doable?
Yeah, I think so. The question is, how can, in what position would be the dipole? What's the orientation?
No, this is the point. You have to make a map.
Yeah, a map. Okay,
you have
got
to
it.
do like a grid of angular grid, and then you go to all of those positions because those are equally probable. So
Yeah, I think it's possible. We can discuss that. We thought about it at that time, in 2008, but we didn't have a student to do that at that time, and then we moved to other. Ah, that's nice. That's nice. So let's talk, Fernando.
Sure. Thank you.
Thank you. Yeah? Any other question?
Yeah. How well does DFT predict the
It can predict as well as Poissonbottom approach, but with other contributions. We can consider the size correlation, for example, the size contribution in a more natural way. So tomorrow I'm going to show some results, not exactly for DFT, but we're going to see how we can get this contribution, the ion-specific contribution. Okay. More questions? Okay, so thank you. Let's go for the... Let's go for the short coffee break and then work groups.